All right, chemistry, let's take a look at chapter 10. We're going to start with section 1, that is the kinetic-molecular theory of matter, and we are going to focus on a very specific phase of matter, that is gas. So we are not going to go over the kinetic-molecular theory of matter in general all that much because it does apply to solids and liquids, but with this unit being comprised of chapters 10 and 11 in our textbook, we are going to focus on its application to gaseous states. So at the end of this section, section 1, I want you to be able to state the kinetic-molecular theory of matter and describe how it explains certain properties of matter. Then list 5 assumptions of the kinetic-molecular theory of gases. Then describe each of the following characteristic properties of gases: expansion, density, fluidity, compressibility, diffusion, and effusion. Note the first objective in light of the third objective. The third objective gives you characteristic properties. And the first objective asks you to describe how the KMT explains certain properties of matter. Those are the 6. Those are the 6 properties of matter I want you to be able to explain using the kinetic-molecular theory. Then lastly, I want you to be able to describe the conditions under which a real gas deviates from ideal behavior. So let's get started. So the kinetic-molecular theory is based on the idea that particles of matter are always in motion because, well, they are. The theory can be used to explain the properties of solids, liquids, and gases in terms of the energy of particles and the forces that act between them. An ideal gas, okay, this is going to come in handy when we're trying to explain why real gases actually deviate from ideal behavior. But we define what an ideal gas is by saying that it is a hypothetical gas, meaning it does not exist in real life, but it perfectly fits all the assumptions of the kinetic-molecular theory. Now, there are gases that very, very closely approximate all 5 assumptions of the kinetic-molecular theory, but there are no gases that perfectly fit all 5, right? So there's a difference between ideal and real. So the kinetic-molecular theory of gases is based on the following 5 assumptions. 1, gases consist of large numbers of tiny particles that are far apart relative to their size. That means if they're very, very far apart from one another, that means most of the volume occupied by a gas is actually empty space. It's the empty space between the individual particles. Number 2, collisions, right? Because these particles are in constant motion, and so obviously eventually they're going to come in contact with one another. They're going to hit each other. They're going to hit the container walls. And so collisions between gas particles and between particles and the container walls are elastic collisions. An elastic collision is one in which there is no net loss of kinetic energy. Even if the kinetic energy of one gas particle is transferred to the other particle, because we're talking about the net system, all of that kinetic energy was successfully transferred to this second particle. So net, there is no loss of kinetic energy. Number 3, gas particles are in constant, rapid, random motion. They therefore possess kinetic energy, which is the energy of motion. Number 4, there are no forces of attraction between gas particles. And realize in that general concept, no forces of attraction, we're also saying that there are no forces of repulsion also. And number 5, the temperature of a gas depends on the average kinetic energy of the particles in the gas. But the kinetic energy of any moving object is given by the following equation. Kinetic energy, Ke, equals 1/2 mv squared. That's mass times velocity. Now, all gases at the same temperature have the same average kinetic energy. Doesn't matter what the gas is. If they're all at the same temperature, the average kinetic energy is the same. But going back to that equation, if the kinetic energy is constant, but the masses vary, that means in order to maintain the relation, equality, it means that the velocity is going to have to change to make up for that. So at the same temperature, therefore the same average kinetic energy, lighter gas particles have higher average speeds than do heavier gas particles. For example, hydrogen molecules have a higher speed than oxygen molecules.
The kinetic-molecular theory describes the behavior of gas molecules and the physical properties of gases. The kinetic-molecular theory views gases as being made up of large numbers of fast-moving particles that are far apart from each other. Most of the volume occupied by a gas is empty space. Gas particles are in continuous rapid random motion, and the forces of attraction or repulsion between them are essentially non-existent. Kinetic-molecular theory relates the kinetic energy of gas particles to the temperature of the gas.
That last portion of the video that was not flowing so well was supposed to indicate as temperature increases, the velocity and frequency of collisions of the gas particles with the container wall increases, increasing the pressure, and in that example, providing so much pressure that they're able to pop the balloon.
Gases differ from solids and liquids in that they expand to fill the shape of their container. Because there are large distances between gas molecules, gases have extremely low densities. Carbon dioxide, for example, is less dense than water, so bubbles of carbon dioxide rise to the surface. Gases are compressible to small fractions of their initial volumes. Because of this, large amounts of oxygen can be stored in tanks for scuba diving. Gases mix readily by diffusion. We don't have to stir or shake them to make them mix. Gases can escape containers through tiny holes in a process called effusion. This occurs when a bicycle tire is punctured.
So let's look at the nature of gases as explained by the kinetic-molecular theory of gases. And so what we're going to do here is we're going to look at those 6 characteristic properties of gases that you need to be aware of. Not only do you need to know what they are, not only do you need to know that gases show those characteristics, you need to be able to explain why gases show those characteristics using the kinetic-molecular theory as an explanation. So, the kinetic-molecular theory applies only to ideal gases. Many gases, like I've said before, behave nearly ideally if pressure is not very high and if temperature is not very low. So let's get into these properties. Expansion. Gases do not have a definite shape or a definite volume. They will completely fill any container in which they are enclosed. Gas particles move rapidly in all directions. That is according to assumption 3 that we've already stated. Gas particles move rapidly in all directions without significant attraction between them. That means that they will expand outwards to fill the container. That is expansion. Fluidity. Because the attractive forces between gas particles are insignificant, right? That's assumption number 4. Gas particles will therefore glide easily past one another because they're not being hooked on to one another or repelled by one another. This easy sliding past one another is referred to as flowing. Both liquids and gases flow. Because liquids and gases flow, they are both referred to as fluids.
A fluid is a substance in which the atoms or molecules are free to move past each other and can therefore take the shape of their container. Liquids can take the shapes of their containers. Therefore, liquids are fluids. Gases can also take the shapes of their containers and are therefore also fluids. An ideal gas behaves as described by the ideal gas equation PV equals nRT. There are several assumptions about the nature of a gas that are required for it to behave ideally. A key assumption is that the gas molecules occupy no volume. In a real gas, the molecules have a small but positive volume. Another important assumption is that kinetic energy is dependent on temperature. This means that the molecules are moving at a speed dependent on temperature. Real gases have molecules moving at a variety of speeds. Ideal gases collide like billiard balls and bounce off each other while maintaining their speed. They do not stick to each other or their container walls. Real gases occasionally stick to each other or the container walls. Ideal gas particles are always moving, but collisions that lead to sticking can cause real gas particles to violate this rule. Ideal gases do not attract or repel each other. Sometimes real gases do attract or repel each other.
Next characteristic, low density. The density of a gaseous substance at atmospheric pressure is about 1/1000th of the density of that same substance in the liquid or solid state. The reason is that the particles are so much farther apart in the gaseous state. Remember assumption 1. They're very, very far apart from one another relative to their size. Because of the low density, because of their expansion, they have the capacity for compression. During compression, the gas particles, which are initially very far apart, again, assumption 1, are crowded back together. The last two, diffusion and effusion, are often dealt together because they are pretty darn similar, but there's a key characteristic, and it's pretty darn easy to keep them straight, and I'll show you that hint. But diffusion and effusion. Gases spread out, and they mix with one another, even without being stirred. The random and continuous motion of the gas molecules, right, that's assumption 3, carries them throughout the available space. They will expand to fill whatever container they are in. Such spontaneous mixing of the particles of two substances caused by their random motion is diffusion. One way you can show diffusion is by opening, for example, a bottle of floor cleaner that has a heavy concentration of ammonia. And just by opening that bottle, the smell of ammonia will fill the room eventually because the odor, the gas, is filling the room. As opposed to effusion, effusion is a process by which gas particles pass through a tiny opening. And that is the key there, a tiny opening. In diffusion, there's an open space, an open area where that gas is going to fill. It's going to fill that container. It's going to match that shape. Effusion is, again, the movement of gas particles, but here in effusion, there has to be a tiny opening. So the rates of effusion of different gases are directly proportional to the velocities of their individual particles. Molecules, for example, of low mass effuse faster than molecules of high mass, which makes sense because according to the equation, kinetic energy is equal to 1/2 mv squared. When the mass of a particular particle is low, the velocity will increase. And so if the velocity of a particular gas particle is high, it has a better chance of passing through that particular tiny opening. We also need to be able to tell the difference between a real gas and an ideal gas and why those deviations occur. Because particles of gas occupy space and exert attractive forces on each other, all real gases deviate to some degree from ideal behavior because all gases really do occupy space. Might not be that much, but they do occupy space. And they also exert some sort of attractive force on each other. It might not be a whole bunch, but there is some. And remember that the KMT assumes that gas particles have no volume and that they exert absolutely no attractive force on one another. Because both of these never exist in real life, all real gases deviate, again, only to some degree, maybe only to a small degree, from ideal gas behavior. A real gas, on the other hand, is a gas that does not behave completely according to the assumptions of the kinetic-molecular theory. At very high pressures, for example, and very, very low temperatures, a gas is most likely to behave like a non-ideal gas. because at high pressures, we are actually pushing them closer together, closer together. And when two particles are closer together, they have a greater opportunity to experience each other's attractive and repulsive forces, therefore deviating from ideal behavior. At very, very low temperatures, velocities of the individual particles are very, very low, meaning as particles pass close to one another, they're in close proximity for a longer time because they do not exit the proximity very, very quickly, and therefore have an opportunity to feel and experience each other's attractive and repulsive forces, therefore deviating from ideal behavior. Also, on that same line of reasoning, the attractive forces and the repulsive forces existing between real particles, the more polar a molecule is, the more that gas will deviate from ideal gas behavior. Because to say that a molecule is polar is to say that it has attractive forces. So if it has more polarity, a stronger polarity, more intense polarity, that means it's going to have more intense attraction and repulsion. We are also going to squeeze pressure, section 2 of chapter 10, into this video. At the end of this section about pressure, I want you to be able to define pressure, give units of pressure, and describe how pressure is measured. I want you to be able to describe, wrote that twice apparently, describe how pressure is measured, convert units of pressure. There is more than one unit of pressure, and you have to be able to convert between those two units, but because we know about the factor label method of dimensional analysis, that should be no problem as long as we have our statements of equality. Lastly, state the standard conditions of temperature and pressure. There's something called STP, standard temperature and pressure, and you need to know what those are. Let's start with defining pressure. Pressure, represented by a capital P, is defined as the force per unit area on a surface. Gas pressure is caused, the force per unit area is caused by the collisions of a gas molecule, either with each other or with the surfaces with which they come into contact, right, the container wall. The pressure exerted by a gas depends on the volume of the container, because that's going to have an effect on how many collisions there are per unit time. The temperature, because the temperature, again, has to do with the average kinetic energy, and that's going to dictate the velocity of the individual particles. The higher the velocity of the particles, the more force they're going to exert on the container wall. The lower the temperature, the less force they're going to exert on the container wall when they collide. And then obviously the number of molecules present, because if you have more molecules present in a container, you're going to experience a higher frequency of collisions because there are more molecules in there to collide. So that means, in general, the higher the number of collisions of gas molecules, the higher the pressure will be. If you can increase the number of collisions, you'll increase the pressure.
Pressure is caused by the collisions of gas particles with the side of the container. With a large volume, the particles do not collide with the sides of the container very often, and the pressure is relatively low. When the volume decreases, the particles of the gas collide with the sides of the container more often. With more collisions, the pressure increases. Boyle's law states that the volume of a fixed mass of gas varies inversely with pressure at constant temperature. In other words, the smaller the volume, the higher the pressure.
We need to know a little bit more about pressure. The SI unit of force, right? The international system base unit for, it's not base unit, it's a derived unit. For force is the Newton, represented by a capital N. The force that will increase the speed of 1 kilogram by 1 meter per second for every second that the force is applied. For example, consider a person with a mass of about 51 kilograms. At Earth's surface, gravity has an acceleration of 9.8 meters per second squared, right? That means for every second that the force of gravity is applied, that 1 kilogram will accelerate at 1.8 meters per second. The next second, it'll accelerate by another 9.8 meters per second. The next second, it will increase by yet another 9.8 meters per second. The force that this person exerts on the ground, however, because we're talking about pressure, and pressure is equal to force per unit area. So the force that this person, the 51 kilogram person, exerts on the ground is therefore represented by 51 kilograms multiplied by the acceleration, the 9.8 meters per second squared. This equals 500 kilograms times meters per second squared. And the unit, the derived unit, kilograms, multiplied by meters per second squared is a Newton. So pressure, again, is a force per unit area. Okay, so the pressure of a 500 Newton person, right, that 51 kilogram person who is standing on Earth's surface, and all of that mass, that 51 kilograms, is being accelerated down at a rate of 9.8 meters per second squared. That 500 Newton person standing on an area of a floor that is 325 square centimeters, we can calculate the pressure that that person is exerting on the floor. We simply divide, right? Because it's force per unit area. That means force divided by area. So we have our force, 500 newtons. We're dividing by our area, 325 square centimeters. That comes out to a pressure of 1.5 newtons per square centimeter. Realize how we can manipulate this number. If the force on a constant area increases, right? The greater the force, the greater the pressure. Or if we make the area on which that same force acts, the greater the pressure will be. So we can manipulate those numbers, and we can see, because of the mathematical relationship, how those numbers would change. So if we take a very knowable example, a ballerina, if we say, and this is where we got the 51 kilograms, right? If we assume that this particular ballerina has a mass of 51 kilograms, and she is standing at Earth's surface, when she stands on 2 feet, right, the soles of 2 feet, it takes up an area of about 325 square centimeters. Again, that's where we got that number, right? We're actually talking about the bottoms of someone's feet. So if that 51 kilogram person at the Earth's surface exerts a force of about 500 newtons, and all that 500 newtons is being exerted onto the ground through an area of about 325 cubic centimeters, the pressure that she is exerting on the ground is about 1.5 newtons per square centimeter. However, when that ballerina goes up onto her toes, like ballerinas do, the force does not change, right? She has the same mass. She's being accelerated by gravity to the same extent, and so it's still a 500 Newton force. However, we've reduced the area of contact between her and the ground, right? She's up on her toes. We've gone from 325 square centimeters all the way down to about 13 square centimeters. We have the same force because she has the same mass, but we're exerting it on a smaller force. Notice that over those 13 square centimeters, we are now exerting pressure insanely more intense than example A. We're up to 38 newtons per square centimeter. And as ballerinas do, go up onto one toe, we're going to reduce that area of contact by half. Now we're down to 6.5 cubic centimeters. Again, her mass hasn't changed. Acceleration due to gravity hasn't changed. So her force does not change, but the area does. It's even smaller. And so we see, after we calculate pressure, the pressure on that one set of toes is 77 newtons per square centimeter. Now we're going to talk about how pressure is measured. A barometer, a barometer, is a device used to measure atmospheric pressure. The first barometer was induced by a scientist named Torricelli in the early 1600s. Torricelli noticed that water pumps could raise water only to about a maximum height of, again, around 34 feet. And he wondered why this was so. This was an observation that he saw was constant, and he wondered why this was the case. And he thought his idea, his hypothesis, was that the height that water pump could raise the water, right, the 34 feet, the height must depend somehow on the weight of the water itself compared with the weight of the air that's on top of it. Torricelli reasoned that if the maximum height of a water column depended on its weight, then mercury, which is about 14 times as dense as water, could only be raised about 1/14 as high as water, right? If it took 14 times more energy to raise that mercury because it's more dense, then it's only going to be elevated by 1/14 of the rate. And so he tested this idea by sealing a long glass tube at one end and then filling it with mercury. He then inverted the tube into a dish of mercury, and the mercury rose to a height of about 30 inches, which in millimeters is 760 millimeters. However, turns out that distance, that height, is about 1/14 of 34 feet.
Atmospheric pressure is the pressure caused by the weight of the atmosphere. Air pressure changes with altitude and can be measured with a mercury barometer. The height of the mercury in the tube indicates the atmospheric pressure in millimeters. If the atmospheric pressure increases, the air exerts more pressure on the mercury, causing it to rise in the glass tube. Thus, the mercury in the barometer rises with rising pressure. If the atmospheric pressure decreases, the pressure on the mercury also decreases. Some mercury will fall out of the tube and back into the container. Thus, the mercury in the barometer falls with falling pressure.
So as we continue to talk about how pressure is measured, the common unit of pressure is millimeters of mercury. That's why I pointed out that 30 inches is 760 millimeters. And we symbolize millimeters of mercury by writing mm, millimeters, of Hg, which is mercury, millimeters of mercury. A pressure, incidentally, and you'll have to use this unit as well, a pressure of 1 millimeter of mercury is also called 1 torr, in honor of Torricelli, for his invention of the barometer. Pressures can also be measured in units of atmospheres, which is very, very common because the average atmospheric pressure at sea level, assuming 0 degrees Celsius, right, the freezing point of water, is 760 millimeters of mercury. 1 atmosphere of pressure. Now, conceptualize that. If you're at sea level, right, you're as low as you can get. You have 1 atmosphere above you, literally, the atmosphere. There's only one of them, and it is on you, and it's pushing down on you. That is 1 atmosphere of pressure, and so we define it as 1 ATM, 1 atmosphere. That is equivalent to 60 millimeters of mercury, as long as we keep the temperature constant, right? We have to say that it's at 0 degrees Celsius, the freezing point of water. Those two numbers create what we call standard temperature and pressure, which is one of your objectives in this lecture. You have to be able to describe the conditions of standard temperature and pressure. Standard temperature, 0 degrees Celsius. Standard pressure, 1 atmosphere, also known as 760 millimeters of mercury. But atmospheres and millimeters of mercury, or even torr, is not the only unit for pressure that is used. In the SI system, pressure is actually expressed in pascals. 1 pascal, represented by capital P lowercase a, is defined as the pressure exerted by a force of 1 Newton acting on an area of 1 square meter. This unit is named after a French mathematician and philosopher who studied pressure during the 17th century. But 1 pascal, right, 1 Newton per 1 square meter, is actually a very small unit of pressure. So in many cases, it's actually more convenient to express pressure in kilopascals, right, 1,000 pascals. For example, 1 atmosphere, right, that standard pressure, 1 atmosphere is equal, there's a statement of equality you can use for a conversion factor, 1 atmosphere is equal to 101.325 kilopascals. And here are all of the conversion factors that you will need to do any conversion of units that you will find in this section. So let's try to use them. The average atmospheric pressure in Denver, Colorado is 0.830 atmospheres, right? It's pretty elevated. The entire atmosphere is not above Denver, Colorado because it's so high. Express this pressure in millimeters of mercury, right? mmHg, and kilopascals, kPa. So we've been given atmospheric pressure. It is 0.830 atmospheres, and we want millimeters of mercury, and we want kilopascals. So for that first thing that we're being asked to do, to convert between ATM into millimeters of mercury, we're going to have to set up our conversion factor according to the factor label method of dimensional analysis, the exact same thing that we've been doing so far. We're going to be given a value in ATM. We multiply that by a conversion factor. Now the conversion factor has to be a fraction that is equal to 1, meaning whatever I put on the top has to be equal to what's on the bottom. But we just defined 1 atmosphere as 360 millimeters of mercury. We also just defined 1 atmosphere as 101.325 kPa. And so we have conversion factors that allow us to convert from this given ATM, this given atmospheres, into millimeters of mercury and into kilopascals. And so when we plug in the values that we're actually given, it's very, very easy, very, very simple. Even more simple than the stoichiometry that we've already covered in Chapter 9. Whoop, too far. That's as far as we're going this go around. There's only one more section in this entire chapter, so let's not get ahead of ourselves. We're focusing on the kinetic-molecular theory of gases and pressure. We want to be able to explain the properties of gases using the kinetic-molecular theory, and we want to be able to express pressure in multiple units easily. All right, chemistry, I will see you next period.